The first lecture on major theory. This is the first lecture on major theory. Actually, this is in probability 2. The two sections of probability 1. This is just usual probability, and the other part is major theory. Basically based on set theory and measures. It's mainly set theory thing. Probability actually builds on the set theory thing. So, today class is on sigma-algebra. So sigma-algebra or sigma fields, algebra or sigma field, same thing, same name. This field is not that field in vector space. In vector space, we know there is a field. Field is a set with two operations, addition, multiplication with some properties and distributive, associative, commutative. There the sub identity element and existence of inverse, etc. But this field is not that field. This is sigma field is a different thing, totally different concept. So before going to this sigma field or sigma algebra, I discuss on very simple some notations. What are the basic notations in set theory? So the notations in set theory is very important. Notations in set theory. So we need some notations. So notation in set theory. So we know what is set, and we know it is a union of two sets, say A union B. Just set all X in some, if A and B are to any some universal set, say it may be a subset of universal set, two subset of universal set. Then that universal set S, and A is a subset of S, and B is a subset of S. So both are subset of S, and A union B is just defined as X belongs to S. X is either in A or in B. Sometimes we write this notation also. Other than this, this is the notation for all. You know this. And A intersection B, X belongs to S, X belongs to A, and so must be satisfied both. So it is and means is both true, then this and statement is true, and or means is one of them is true. If both of them true or one of them true, one false, then this or statement is true. Now the important thing is, there's some sequence or collection of events. It may be infinite collection. So the question is, what is the collection of sets? Now it is a set of sets. It's a collection of sets. It means a collection of sets means a set of sets. So it may be powers. It may be any arbitrary collection of power subset of. So collection. It may be finite. It may be infinite collection. The set may be finite. Set may be infinite. If set is finite, that collection cannot be infinite, because if set is finite, the universal set is finite. There are 2 to the power n many subsets. We know. So the collection has to be finite. But if it is infinite, it's a real number or natural number. Now the number of subsets is infinite. So you may take some finite sets or maybe some infinite sets. The collection may be finite, the collection may be infinite. So it's a collection may be finite, it's a collection of 5 elements. And among the five sets, subset, there are say 3 are infinite, 2 are finite. It may be the collection itself is infinite, and the all the subset, that elements are now is a subset. The element of the collection is a subset. So that subset may be finite. So the collection is infinite, but every element is, remember, the collection of set, the elements of the collection of set itself is set, subset of this real number or natural number. That may be finite. So this collection sometimes written as say collection by the indexing thing. Collection is sometimes script A is a collection of some sets A alpha. So A alpha is maybe a subset of some S or some universal set. This collection sometimes writes in this notation. So what is lambda? Lambda is called index set. It's called index set. So this is a subset for all lambda basically. all alpha in lambda. So that lambda is a index set. This is called index set. For example, say lambda take say 1, 2, and say 7. So lambda is 1 to 7. Then your collection is just A1, collection of A1, A2, and A7. It's just 3 elements in this collection, and all the elements are set. Remember, all the elements are subset of S. So this collection may not become integer. Maybe sometime collection maybe say -2, say half, say pi, or maybe minus e. The collection is just a minus 2. A minus 2 is the index. Remember, it is a minus 2 is set. Remember, a minus 2 is just a name. The name of the set is -2. So name of the previous set is say 1. Another name of the previous set is say 2. Like a roll number. Some roll number is 1, 2, 7. Some 1, 2, roll number is -2. So the name, this is, remember, this a half. So a half itself is a subset of S. It's a name. You can say anything. You may say it is just a say cow, or you may say it is a tiger, or you can say it is a West Bengal. Whatever, it's just a name. Remember, a half is just a name. But a half is a set. A half is a subset of S. If S is a real number, collection of all real numbers. So a half maybe a itself is a subset of real numbers. So a half just say set containing 1, 3, and may not be half there. May not be half. May not belongs to the a half. Like a pi and a minus. These are the 4 sets. All these are index. This is nothing deals with the member of this element. So pi is just a name for this a pi, like a1, a2, a3. May or may not should set a pi. So this is the idea of index set. And now, if index set is 5, what? Index set is 5. This we collect 5. No set is. So if cardinality of the index set is finite, then it says cardinality or number of element of lambda is 7. That means there are 7 subsets in this collection. So this is the one notation to write. Now, what is called union in arbitrary thing, or union and intersection. So union is like that. So if you have a collection of these subsets, it's indexed by lambda, then union sometimes write this. This is the one notation. Some other notations are this. This same thing. This same notation. This, or we can write more elaborately alpha in this index set. Once this index set is clear, we just write this. And sometimes we write if index set is not, if index is what index set, then we just write like that. So like a summation I. We sometimes write summation, just write summation AI. Sometimes let's say summation I AI, but the actual notation is summation I equal to 1 to n AI. The last notation is the actual, the middle notation. But we can use if you understand what is this. So what is the definition of this? Actually, what is the definition of this? The definition, what is the definition of this collection? The collection of this definition for all S. If it is a set of, it is all a subset of S for all this lambda. Lambda is the index set. Lambda is any index set. Index set. Remember that lambda may not be 1 to 3. Lambda may be something like that. So maybe say dog and cow and cat. So then their name of the sets are a dog. The is called a dog. A dog is a subset of a real number. A cow, a cat. So these are 3 sets. A dog may be the set of this is a subset of real number. So it may be say 1 set 1, 2, and say 7. A cow may be say whole natural numbers, and a cat may be 5 set. So this is the index. Index may not be a real number or an integer or anything. It may be abstract. A set itself may be abstract. That all alpha may be a subset of any abstract set, something like a cow, West Bengal, Bihar, something like that. So these are set of all this x. This s may be abstract, may not be real number or maybe complex. may be set of functions, set of matrices, everything. Such that that means X belongs to one of these. If it is two of two, A union B, X belongs to A or B, at least one of them. That means X belongs to A alpha for some alpha, for some alpha. But this notation is very bad for some. The actual notation is, actual terminology for actual thing is this: there exists an alpha. This is the mathematical notation. There is an alpha in lambda, such that if there exists, we should write that such that your X belongs to A alpha. So there is at least alpha in lambda such that X belongs to that. Similarly, what is the definition of this? Intersection. Is arbitrary intersection. This is again clear. You can write just this collection. So it is again is X belongs to X such that A alpha X belongs to alpha for all alpha. Now it's for all. It should be this X must belong to the A alpha for all alpha for every subspace. It should, that is just. So again, if lambda is the collection is phi, their union, because collection is wide, so union is phi, and intersection will take as a universal set. This take as a universal set. If this lambda is phi, then we just say union is. So now here it is interesting. Union is a subset of intersection. We know that the intersection is a subset of union, but in the special case when it is phi, we just by definition we will take this union as a phi, and in this case it is just for completeness. We are never use this actually. Should not use something like phi intersection. Phi, the collection is itself phi, but sometimes maybe is arise. That's why we define it. So you can just for now forget this. If required, then we again discuss on that. Now, the important part is the De Morgan's law. We know the De Morgan's law. De Morgan's law in set theory is very, very important. So if there is any collection and the complement is basically just if the index set is alpha lambda, their collection is this, and you take the complement of this. It's clearly nothing but what is this. Oh, sometimes there is one more notation for that. This sometimes there is a notation. Just A belongs to A. This also a notation. There is one more notation for this for union. This sometimes we write A belongs to this. Is a union of all A. So this is not fixed A. In the union of all A, so that this A are running in this collection. Now, what is this? This is just intersection of A complement or A alpha complement alpha length. So there's again for intersection there are three different notation for intersection. I just write only one. There are three different notation for intersection. So this is a very important thing to understand first. Now we'll go to the sigma-algebra. What is sigma-algebra or sigma field? This is a very, very important thing. So before going to the sigma-algebra, we just give a definition of slightly easier version, easier concept is called algebra, just algebra. Algebra field. This field is not that field in abstract algebra theory field or vector space. This field is different. We are going to define. That's why we sometimes use sigma-algebra or algebra instead of saying just field or sigma field. You should be very clear about it. There should not be any confusion with that field and this field in there abstract. Now, so this is a non-empty set. And you have a collection. You have a collection of, this is a collection of subsets of Now this maybe phi actually is set, just is a set, because if it is phi, then collection is just only element phi. The collection itself contains element phi, only one element. So if it omega is phi, then the power set has just one element, 2 to the power 0 many elements. So only the phi is the only subset of phi. So in the collection, the collection itself may be phi, or maybe the collection contain the phi set. There are two collections actually. So what is the collection of subsets? So for example, say if for example, say if omega is just a set containing say 1, then what are the subsets? The subsets are, the subsets are this itself omega and phi. And what is the power set? The power set of this omega is a set containing phi and this one. Two elements in power set 1, because there are only one. So collection, how many collections are there? So collection are there 4 collections. The one collection is say just 5. No, nothing is there. Another collection may be just set containing just 5. You just take the phi set only. This has no element. And another contains say just set 1. And another is just take both. So there are 4 different collections. Phi and, because is a 2 subset, we can choose collection 2 to the power 2 again. So it's just 4. There are 4 different collections. One collection is just 5, no element. 2 collections are just only one element, phi, and another is just only one, omega. And another set, take the power set of the power set. The power set. Sorry, it is a power set. It's a power set of the omega. Power set of the omega. So these are 4 different collections. We choose any one set. Now, if there are 2 elements, omega 1 and 2, that means the number of subsets 2 to the power 2, which is 4. So number of such a distinct collection is 2 to the power 4, 16. It's a huge. It's a large. It's a 2 to the power 2 to the power n. So in omega there are 5 elements. Then the number of subsets 2 to the power 32. So different collections of subset is 2 to the power 32 is a huge. It's more than 100 crores. It's more than 10 to the power 9. So it's a large number of distinct collections are there. So take anyone, just anyone, and we can take anyone, anything, any one of this. Now, what is field? So field is a collection. Field or algebra is a collection of subsets of omega such that, so there are 4 different collections, but these 4 different collections, all 4 may not be field or algebra. There must be some condition. What are the conditions? The conditions omega must belong to that. So this is not a, this is cross. This is a collection. This is a collection. This is no doubt this script F1, script F, script F3, all a collection of subset, but these are not field. These are not in the field that omega must be there. Number 1, cannot be non-empty. Now, if A belongs to this collection, then you just write in if-then form. There are 2 different forms, implies form and this. Then A complement must belong to that. So there is another form is A implies A complement belongs to this. So just you can say you can write in if-then form or in imply form. Imply form is a better form, is more mathematical, and you know what is the truth table for this simplification. That everything this simplification imply this, implied by, implies or implied by, both side implies, and or negation all have some truth value, the truth table that. And when this is true, you have to prove using that. If I ask you what is true, you should prove that using the truth table only. Other than given the truth table, this proof is not complete. But where proof is in other way, other algebraic way, because every time if you go into truth value by truthness of the statement by truth table, it is very large. It is very complicated, time consuming. But you should know how to write a proof using truth table. That is the ultimate. If you can't write a proof using table, then you don't know the proof actually. Nobody asks you that write in proof using the truth table. But if you can't do this, that means you don't know this. This B belongs to the this is the, so that means the only case is this, that the powers, no other choice for our algebra. And the other thing is, if there A1, A2, n, the n many subsets are in this collection, maybe 100, maybe finite, but maybe 100, maybe 1 core, maybe 10 cores. Then there are unions. Again, this union notation is, this notation. What is the notation? This notation is just A1 union A2 union A. Like in this union notation, if say your lambda is something that set 1, 2, 3 up to n, or 10, 20, or 1 core, that means your A alpha union of alpha belongs to this, nothing but this alpha equal to 1 to n A alpha, which is actually A1 union A2 union AN. Similarly for the intersection, and similarly for the natural number, this is a natural number. If you write alpha belongs to the natural number A alpha, that we write in the collection like alpha equal to infinity. So if you write alpha equal to 1 to infinity, that means this alpha belongs to the natural number. So it is an infinite union, because the index set itself is infinite. The index set is natural number here. So if this property, the three items true, then we say this is an algebra. So if there is set containing just only one element, there is only one sigma algebra you can form. So go with the next one. Say if your omega is say 2, for example. So if omega is 1 and 2, it contains 2 elements. It may be cow and dog. So what are the different subsets? There are 4 different subsets we know. So how many collections may be? So 2 to the power 4. So it is 16 many collections. So the different 16 collections are there. So in collection, you should put omega is your collection, number 1. Next, omega is there. So the omega complement is 5. 5 must be there. So this 2 must be there. Now, you may not take any other thing. Just this is a collection. So this is a sigma algebra. This is algebra. This is algebra. One more algebra is like that. You have to take these 2, and you just take this set. And once you take this set, you have to take the complement of that. The complement of set containing 1 is just set containing 2. So this is a and you have to take the union also. The union of these 2. So union is just omega. So okay. So it's a sigma algebra. It's a what? Any other collection? Any other collection is there? No, because this is the only 2 collections. Because we already take all 4 elements. This collection of subset cannot be more than 4, because there are only 4 subsets. So we took all these things. So it is just a power set. The power set is the maximum thing, and this is the minimum, the first one. So just only 2 collections is a algebra. Among these all 16 collections, if you take just omega and set containing 1, this is not a sigma algebra. This is not an algebra. So this is one more example. And if you have a set of 3 elements, then it is going large and large and large. So So this is clear what is sigma-algebra. What is algebra? Now we are going to define sigma-algebra. Before going to define sigma-algebra, we have a one theorem or one result. If this is a sigma-algebra, is a sigma-algebra or sigma field of on omega, the omega is the set, and if a1 a2 dot 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 dot, by the way, since this is a sigma algebra, but still your omega is infinite. I will give you one more example for infinite case. So if this is in sigma algebra, all this a1 a2 n in the sigma algebra, then the intersection also in sigma algebra. Why it is so? In the definition, this is not taken, because in definition we choose just we say the union must be there, but now I am claiming that the intersection must be there. Why this intersection must be there? This is very easy, because since AIs are there, AIs are in collection, so their complement must be in the collection. So their complement in the collection, so their union in collection, because union must be in the collection. And what is this union? This union nothing but the intersection, and then Morgan's law is just complement of this all inter. Now, if this is the in omega script tape, then the again their complement, which is the complement of this complement is the intersection, then their complement, this set, and you take the complement of this set again. This is nothing but this set. This is in script tape. This complement must be there. So the intersection must be in this collection. So it is trivial, very very easy. Now we are going to define sigma algebra or sigma field or sigma algebra. Now again, this is a collection of is a let this is a B. The let we should write B. Let script F be a collection of subsets of a set omega, then collection is called a sigma field or sigma algebra if and only if, definition is always if and only if, right? If, that means it is if and only. Because if I write in the theorem, if I write if, it is not if and only. But if theorem, yes, if in definition, if I write if, that means it is if and only. Remember, again, the if does not mean that if and only. In for every statement, in any statement, if and if and only is a different thing. But for definition, if I write say if, that means if and only. So we just write if for definition only. So if and only for number one, same thing. This number two, the same thing. If A belongs to this, then A complement also belongs to this. The same as like algebra or field. The third one is different. If there we choose a finite collection. Now we are taking an infinite collection. So infinite is now natural number. Your index is natural number. If all R belongs to script F, then this union, that is alpha belongs to the natural number alpha, or that is right in this form I equal to 1 to infinity. The same thing. This is in script F. So this is the difference between sigma algebra and algebra. In sigma algebra, this is a finite. It's clear by the definition. It is just that if this omega is finite set, omega itself is a finite set, then the concept of sigma algebra and algebra same. Algebra and algebra coincident. These two concepts. Why? Because since the set is finite, the number of subset is also finite. So you can't have any infinite collection. So the collection always is finite. So your sigma algebra and algebra is the same concept. The question, if there is omega is infinite, then the collection may be infinite. In that case, some collection is infinite. That union may not exist in the, but finite union of the finite collection is in the collection. Then is a algebra, but it's not sigma. So we should give an example of algebra which is not sigma algebra. But this example is not easy. This is like a non-trivial example. So how do you give an example of sigma algebra which is not algebra? So this is not trivial. This is like not trivial thing. You should do with a infinite set. Should not be do with a finite set. So example. So, example of if is a algebra or field not a sigma. So this is slightly non-trivial. Now you have to take this a infinite set, obviously. So take the natural number. We take natural number set, and you want to find a we take a collection of this subset of natural number, but we should not take finite collection. If you take the finite collection, then the concept of algebra is the same. So what will be the infinite collection such that there are infinite collections? Then the union of the infinite collection is not in that collection. Now for this, we know what is finite set. We know what is the definition of finite set. If what is called finite set, but the definition is a term is called cofinite. That is a different term. It is not of infinite. It's called cofinite set. Cofinite may not be infinite. Cofinite may be finite. So cofinite set. What is cofinite set? A is cofinite set if and only if, that means by if and only if, it means if and only if, because it's a definition, the complement is finite. So if the complement is finite, then the set is called cofinite. So interestingly, that if the set is infinite, the complement finite set must be infinite. If set is finite, if omega is finite, then the cofinite is also finite, because every subset is finite. So cofinite is finite. The complement is finite, then maybe it is finite. So complement is finite, the set may be finite. If A is finite, A complement may be finite. But the set is infinite, it can't happen. So cofinite must be infinite. But there are several sets which is not cofinite at all. Itself, it is a finite. There are several sets which is not a finite and not a cofinite. It is not that they're either finite or cofinite. There are sets which is not finite, not cofinite, like a set of even numbers. Like a set of even numbers is not finite and it is not cofinite at all, because the complement of the set of even numbers is odd numbers. This is also again is infinite. So the A is infinite, the complement also infinite. So that means A complement both are not finite, cofinite. So you just take the collection. Script F is the collection of sets, finite and cofinite sets. Just the collection of finite and infinite set. Just take these collections of what are. Now is omega belongs to there? Yes, omega is infinite. Sorry, if a collection of finite and cofinite. Is omega belongs to there? Yes. Yes. Why? This is infinite set. Complement of this is, oh, by the way, phi set is finite. We call phi as a finite set. Complement is phi, so it is is a cofinite. So natural number is cofinite set. Eventually, any set is a itself is a cofinite set. If omega is a cofinite in omega. So we have this number one. Number what about the B? So if A is in descriptive, is the complement there? Yes, because if A is finite, complement is cofinite, and if A is cofinite, then complement is finite. So we know all finite and in cofinite sets are in this F. So their complement also in this. So if A is finite, then A complement is cofinite. If A is cofinite, then A complement is finite. Now the next one is important. If you have a finite collection, is that union is belongs to this in this collection in belongs to this? This is a important question. The other two is very easy, but this is the most important, the crucial part. Yes, it is true. It's true. Why? So we have to prove that. So what you have to prove? So you have to prove that if you have a collection of finite and infinite cofinite set, finite collection of finite and cofinite set, some are finite, some are cofinite, that union is finite or cofinite. Now, if the all are cofinite set, so the case one, if all are finite, then union is also finite. Because there are finite union. So finite union of finite set is infinite. Now, if one of them is cofinite, if say one of them is cofinite, AI is cofinite, other may or may not be cofinite or finite. If just one of them is cofinite, then the union is cofinite. If all of them are finite, then it's finite. If one of them is cofinite, then this union is cofinite. Why? This is again easy. Why this is so? You have to take the complement of that. You have to find the complement. So complement of this set, and you have to show this is finite. Then it is cofinite. So what is the complement? Again, the De Morgan's law is a very useful and important set theory. You know, this is the complement and the intersection. Now, what about now this? What is say? Okay, you just use I, so you will say another notation for say J, for some J, or some J in 1 or 2n. Say a 10 is a cofinite. Now what is this? AJ complement is finite. Now you know this is a subset of AJ because the intersection of A1 intersection A2 intersection A3 dot, 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 so it must be subset of every set since an intersection. Now AJ complement. So since AJ is itself finite, this is finite. So since this is finite, this is also finite. Subset of a finite set. So complement is finite. That means your collection of this, if is a one of them is cofinite, and if you take the intersection, that will be a union, that will be a cofinite set. Now, so it is a sigma-algebra. So therefore, this collection is algebra or field. No, but this is not sigma-algebra. Why? Why this is not a sigma? Now you have to you have to find some set which is finite or finite, but the union is not finite or cofinite. Now this is again trivial. So you take a collection like that. So your collection is say AI is just the element of just 2i, not 2i. So your 1 is just set containing 2. Your A2 is just set containing 4. Just only one. Now these are all finite set, right? But the infinite union, this is a set of all even numbers. And this is not finite, not cofinite. And this does not belong to this script F, but each R belongs to this script. Each sets are belong to F, but their union, the infinite union, is not belongs to descriptive. So that's why the set of even numbers is not finite, not co-finite. So that's not in the collection. That means this collection is not a sigma-algebra. So here we is a example why it is sigma-algebra and algebra is a different one. Again, if omega, the mother set, the universal set is finite, then the concept of this is if it is a sigma-algebra, it must be a sigma-algebra. In the first example, in the previous in the first slides, or we say this algebra. Sometimes I say the sigma algebra, but it's again it's algebra and sigma algebra both. This is one thing. Number two, if the collection, this scripted, is a finite, then again, if it is a sigma algebra, this is algebra, then it's a sigma algebra. Because you can't take an infinite union from that collection of subsets, because the collection of subsets itself is a finite. The set may be infinite. So we have to very carefully choose two things. Number one, you have to choose an infinite set, number one, and you have to choose an infinite collection of subset of that infinite set, which are going to be as algebra but not sigma. So this is the basic idea and basic difference between algebra and sigma algebra. Now I give some examples of sigma algebra, which is obviously a sigma algebra is algebra. So again, the trivial result is sigma algebra implies that, but otherwise not true. It is algebra may not be sigma algebra. Why this is true? If sigma is an algebra, because if an infinite collection is union of the collection belongs to that, why this finite collection would be there? That's the question. We know, okay, these are if this hold dot dot dot, then the infinite union is there. But how do you know the finite union is there? This is very easy. So take finite collection, say a1, a2 dot 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 an. This a1 may not be the previous one. A1 will be the say a10 or a10, a15, whatever. Now you have to unit in F, but I don't know. I just know that if it is infinite collection, then it is true. The rest is very easy. You just take the like that union a2 dot 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 an, and rest choose a set. An plus 1 this choose a set, which is same as this. Now we know this since it is an infinite collection, it belongs to script because it is sigma algebra. Since it is sigma algebra, this infinite union is infinite collection of union is in this script. But this infinite is nothing but a finite union. So that means the sigma algebra is an algebra. But the other way not. If the finite union is in this set, the infinite union may not be in this set, like a finite thing. So this is one thing, and again one more thing is this. One more result is very important, and again it is trivial by De Morgan's law. So it is if a1, a2 dot 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 in F, if F is a algebra, then their intersection also in script. Is again it is just using this result because the intersection. Sorry, why I did complement intersection. It is just a1 intersection over all this I equal to 1 to infinity is nothing but you just take the complement of all I, take the union, and they take their complement. So this is De Morgan's law. And since AIs are in F, the complement is in F, the unions are in F, again the complement is again F. So in F. So this intersection. Now, up to this, it is very, very easy. Now, we are going to slightly complicated. This is very trivial. This is very interesting, very easy thing, just a definition and some example and very few trivial results. Now we are going to slightly complicated thing, not too much complicated, but slightly complicated thing. We will give an example, not elaborately. It is actually analysis. We will do this, the elaborate thing. It is not. There is no scope to elaborate discuss here. So it's called Borel sigma. So now we are going to define a sigma-algebra on R. How do you define a sigma-algebra on R? Again, you just take phi and R, the collection of phi and R. This is obviously the sigma-algebra is the algebra. Okay. Now this is a good version of sigma-algebra is this Borel sigma. This Borel sigma-algebra is in the next lecture or next we'll discuss elaborately. But here is introduce Borel sigma-algebra just vaguely. You just take all this, so say A less than B, say, okay, you can take A equal to B. If A equal to B, then that means this is a phi set, basically. Phi set. What is the whole set? So, and AB in the R, real number. Now this, collect this all in F, script F. So, all right, this is called Borel sigma, is not in script F, this right script B, like Borel, so it's script B on R. It is again on this on R2 or in Rn, or maybe in sequence space R infinity. So it is much larger space, but in R it is a Borel sigma algebra on R. So this is a collection of subset of real number, not the all subsets, some subset, but it's a huge collection. It forms a sigma algebra over R. Collection containing this type of set. All this half open and one side half open closed. And they're all complements. What is the complement? The complement of this set is minus infinity to A union B to complement of this. These are also in complement of this. And they're all sorts of infinite union. So they're all unions, then complement. You can take again complement. You can take again union. You can take again complement. Again union. You can go anything. So this now your collection will be huge. Now their collection is larger and larger and larger. So it's a huge collection. So this collection is called Borel sigma algebra. Then every element, the elements or any set in the elements of Borel sigma algebra is known as Borel set. If I say Borel set, that is a in the element of the Borel sigma algebra. That means it can be formed. It can be formed starting from sequence or infinite collections of sequence of this half open, half closed, and taking their complement, take their union, again complement, again union, like that, and you are reaching set. Like this set is also in your script. Why? So I just only one group, and later we'll see why there are other several types of sets. We just give us this. This is not trivial, but it is easy. Why this is a Borel set? This is a collection of Borel. You have to show that this type of set, say A less than equal, is this set is actually belongs to. It can be formed using the complement or union of this all sort of this half open, half closed set. Show this, and this is easy. But is an intersection of all n equal to 1 to infinity, A minus 1 by A to B. If you take this intersection, you will exactly just precisely get this both closed interval. I have to show this. This check is homework. Check. This is so there's a set Borel set is there. So we're not going to in this direction. Later we'll see in this direction. Now we have one more notation. I'll this class. This notation is called actually limit of sets. This is very, very important concept, limit of sequence of set. Now we know what is sequence of real number. Now it is not a, it is a slightly complicated sequence of sets. So collect A1, A2 is a sequence of set. Sequence of set. Everyone is some omega subset of some omega. It may not be in the sigma algebra. Sigma algebra not here. It's purely set theory again. Is forget the sigma algebra now. Now limit. Now there is a different concept of limit. Here, there are two types of concept: limit, lim sup. One is called lim sup, and one is called lim inf. This is called lim sup and lim inf. Sometimes it's write as lim sup of this, inf of this. A. Now this is slightly complicated. I can just define this as a. I can give the definition, but you have to give some motivation on that. So motivated why this super we some real analysis part. So we need the lim sup and lim in the in real analysis. So in real number. In the next class, in next lecture, I'll discuss elaborately on that. First discuss what is the limit and lim sup limit in the real sequence, and then we get the motivation and we get the similar in set theory. But I just before stop this lecture, we just give a thing that if A1, A2 is an increasing sequence of set, is increasing sequence of set. It's called increasing sequence of set. Sometimes like n increased, if it increased, something like increasing sequence of real numbers, say 1, 1.1, then 1.2, 1.3, 1.5, 1.9, something like that. And maybe there's same concept like a decreasing sequence of set. It's maybe decreasing sequence of set. Decreasing sequence number, right? We write this. Now, in that case, if n is an increasing sequence, then we define a concept. So just is not a limit to lim sup. Once when the limit exists, if lim sup and lim both exist and if they're equal, then we know from the real analysis, if lim sup and lim both exist and equal, then it's a limit exists. Now, then limit exists. What is the limit? In that case, for the increasing sequence, the limit is nothing but an union over all this thing I equal to 1. If you take the all union of all this set, this is the basic define. This is by definition. If I define, we write some colon. Colon means by definition. You can't prove this. Is not? You never prove this. It's just a definition. And if n is a decreasing sequence, then define limit is just limit, not a lim sup. Again, here if it limit exists, lim sup and lim inf are both equal and same as limit. So we are not. This is not the definition of lim sup or lim inf. But we can prove for this, particularly for the increasing and decreasing sequence, this lim inf, lim sup are equal, and this is the limit. So we just define limit. This is by definition again, intersection of all I equal to 1 to n infinity. I equal to 1 to infinity. Yeah, it's just by definition. These two are limit, and in this class we define what is lim sup and lim inf, and we'll see that in for decreasing or increasing sequence of set, this lim sup and lim inf are equal, and that is same as limit by definition. And we'll next give the example of collection which is not increasing or not decreasing. In that case, we will show that lim sup or lim inf may exist, may not exist. They may, if they exist, may not be equal, may be equal. And if they're equal, then we say that is called the limit. And then this limit is obviously not the intersection or union of all this. It is not a increasing or decreasing. So this is all for today. I give this the next class this all this proof, these definitions. But remember, this set theory is too much important for major theory. I'll stop.